Today, we will be continuing on with energy, talking about power. Power is an amount of energy in a certain amount of time. If you have an engine that can output 1 joule per year, well, that's not a whole lot. If you can output 1 joule per nanosecond, well, that's a whole lot better. The amount of energy that you output is related to the power by how much time you have to output it. Power is like salary. Your power is your salary. It's the amount of money you get per time instead of energy per time. That's the relationship between power and energy. One is your salary and one is your total bank account, I guess. So keep that in mind. Energy per time. Well, energy is measured in joules, as we have discussed at length. Time is measured in seconds, of course. And writing joules per second is ponderous. It's a lot of writing out. And so we abbreviate joule per second as a watt. 1 watt. And a watt we can also abbreviate again as just W, capital W. So 1 joule per second is 1 capital W watt. And the power, now see, this is where things are going to get slightly confusing. The power, which is P, can be viewed as, or is equal to, the work. Now this capital W is the work, and work is measured in energy, whereas when W is used as a unit, it's referring to energy per second. And so that is very confusing that we have, yeah, that should be fixed. We have work as capital W as energy and watt as capital W as energy per time. The difference is work is its own measured quantity, whereas a watt is a unit. Work is a quantity that you measure it, and watt is how the units in which you would measure something. It's not great, but it's the system of units that we have. And talking about fixing it, yeah, we can talk about fixing this stuff, but so many people are so set in their ways that it's unlikely to get fixed, shall we say. Power is also just delta E over delta T. If power is work over delta T and work is just delta E, then we can just say power is change in energy over change in time. Power is often measured in kilowatts, and a kilowatt is 1,000 watts, and so a kilowatt is 1,000 joules per second. If you ever see something in kilowatts, that just means that it's consuming or producing 1,000 joules per second. We also see a quantity called a kilowatt hour, which is very different from a kilowatt. A kilowatt hour measures something entirely different than a kilowatt. A kilowatt measures power in terms of how many thousands of joules per second is being used or produced. A kilowatt hour is actually just a measure of energy that is not per time. Even though it has the word hour in it and the word watt in it, this is just pure energy, not per unit time. 1 kilowatt hour is the amount of energy that you would use if you used 1 kilowatt for 1 hour. You might have, the old light bulbs were like 100 watt light bulbs. If you used let's say you used 10 of them, so that you'd get 1 kilowatt. If you had 10 100 watt light bulbs, 100 watts times 10 is 1,000 watts, and that's 1 kilowatt. If you used 10 of those light bulbs for 1 hour, you would use 1 kilowatt hour of electricity. Okay, well, a kilowatt is, as you can see here, 1,000 joules per second. and an hour is 3,600 seconds. So if we take 1,000 joules per second and multiply by 3,600 seconds, then we can see that 1 kilowatt hour, 1 kilowatt for 1 hour, is equal to 3.6 megajoules, 3.6 million joules. That's a lot. 1 kilowatt is 3.6 million joules, and you can buy 3.6 million joules or 1 kilowatt hour of electricity for about 10 cents in the state of Florida. If you look at an electricity bill, it will say somewhere on there that the electricity costs so much money per kilowatt hour, usually around 10 cents per kilowatt hour. It's different in different parts of the country, and it's different in different parts of the world, but it's generally in this kind of range. How do we put this in perspective in terms of powering up an object? Powering something up implies that you're adding energy to it, that you are using it almost as a battery. You need to put so much energy into an object for it to function, for example. At least that's what I think about when I think about powering something up. So that would require a certain amount of energy per time, or a certain amount of power. And if you have a whole lot of power, then you don't need very much time. If you have very little power, you need to hook it up for a long time. So what else can you do with 3.6 megajoules? Well, you can power 10 very large light bulbs for an hour. You can power, I believe, a refrigerator is about 400 watts. One refrigerator takes, on average, about 400 watts to keep it running. And so a 400-watt refrigerator you could run for 2.5 hours with 1 kilowatt hour of electricity. If it's 400 watts, that's 0.4 kilowatts. Then if you have 1 kilowatt hour, it's just 1 kilowatt hour divided by 0.4 kilowatts. And you'd see that you could run a refrigerator for 2.5 hours. You could run an air conditioner for like 30 minutes with 3.6 megajoules. And so, you know, these things add up. After a month of running your air conditioner a whole bunch, then after a month, then you can see how your power bill can be like $100 or something. That's a horrible power bill, but that's what we get for living in Florida, I guess. I've got 2 quick example problems for you, neither one of which are very mathematically complicated, but it takes a little bit of thought, of course, to be able to put things in the right places. These kinds of problems are especially useful for the future engineers that we've got, or really the present engineers that we've got watching. An elevator goes from 12 meters above sea level to 20 meters above sea level in 5 seconds. It can carry up to 800 kilograms. Let's say that includes the elevator itself. How much power does this elevator have? Or more specifically, how much power does it need to go from 12 meters to 20 meters in 5 seconds, carrying 800 kilograms of whatever? Assume the elevator moves at a constant speed. Okay, I've got power is equal to delta E over delta T. I've got the potential energy. Oh, that's the old way of showing it. We now use the U sub G for gravitational potential energy, but that's mgh or mgy. And we've got kinetic energy 1/2 mv squared, but I've crossed it out for reasons. So let's take a look. We've got an elevator that moves from 12 meters above the ground to 20 meters above the ground, and it does so in 5 seconds. It's carrying 800 kilograms total, and we need to find its power. So we rewrite the power equation. Very simple equation right there. The power is equal to the change in energy over the change in time. Remember what we've done with delta E before. Sometimes we say delta E is E final minus E initial. And when we do that, we have to say, okay, what kinds of energy does it have before, at the end and the beginning of the problem? at the end of the problem, the elevator has energy. Well, it's definitely moving. We said that the speed doesn't change. And so the speed, okay, that implies that it's got some kinetic energy final. And it's definitely higher up. So we can say, well, it's also got UG final. And then we have to subtract. Well, we said that the speed doesn't change, so it also had to have kinetic energy initial. And we need to distribute the negative and say UG initial because it was 12 meters above the ground. So assuming that we're setting H equals 0 to be 0 meters, then it's got potential energy, gravitational potential at the beginning and the end. But look at this. I said that the speed doesn't change. So if the speed doesn't change, then that is equal to that. And we're subtracting them. So those will cancel. And then it would just be UG final minus UG initial, which would be MGY final minus MGY initial, blah, blah, blah. And that's what I've really shown here. After I wrote this out, I wanted to add a little bit more detail to it. We can remove the kinetic energies from here. I flipped the order a little bit, just algebraically changed the order around a little bit, but we can get rid of the kinetic energies, and then we get mg height minus mg height over delta t. One thing we can do, which is another thing I wanted to show here, is we can take out the mg's from both of those. So that would be mg times H final minus H initial over delta T. That's just delta H, right? Mg delta H over delta T. Okay? Well, delta H over delta T, that's what your height is changing by in a certain amount of time. But that is indistinguishable from your velocity. If you're changing position in a certain amount of time, well, I'm changing position in a certain amount of time. Hey, I've got a velocity. So, mgv. Power for this elevator is actually just equal to the mass times gravity, 9.8 meters per second squared, acceleration due to gravity, I should be specific, times the velocity that it's traveling at. That's one way of doing it. We'd end up having to find the velocity. And so we'd have to say, okay, I guess it's 8 meters in 5 seconds. And so there's no reason to actually use this equation when we already had that right there, and we can just plug in 8 meters in 5 seconds there and find it just as easily that way. And we end up getting about 12,500 watts, or 12.5 kilowatts. 12,500 watts is equal to 12.5 kilowatts. And if you run this elevator continuously for an entire hour, then it would use 12.5 kilowatt hours. So running an elevator continuously for an entire hour would use that much electricity and that much energy. And saying that a kilowatt hour is 10 cents, that means that running the elevator for an hour would cost $1.25, which isn't that bad. That's not super expensive. We should all be very thankful for having electricity. I encourage everyone, just from a psychological standpoint, to be thankful for the simple things in life that we do have, that we are very fortunate to have. And one of the things that we're very fortunate to have is cheap electricity. So be thankful for those simple things in life. And just one more, but we've really already solved it. There's not much to this at this point. An elevator rises at 0.9 meters per second. That's its velocity. It can lift 1,200 kilograms. What's its power? We already solved this. We totally already solved this because We're saying it's moving at a constant speed. Well, so is this one. We figured out this equation just randomly while trying to solve it. And so all we need to do is take the mass times 9.8 times the speed that we're given, and we should get an answer for this next one. Sometimes these problems are that simple. There's not a whole lot that we can do with power to be confusing. And so this is the basic stuff that the future or present engineers and scientists really need to understand to do well with understanding what power is and how to deal with it mathematically.